Hello, my dear friends. Today we are going to consider another topic on waves, and that is derivation of progressive wave equation. We are going to resolve this by using a simple schematic representation of a wave profile. Let's do that right away. And we're going to consider a simple wave profile using this simple diagram. All right. I'm going to make it as straight as possible. Okay. Now, if we have something like this, okay, and then, all right, we are trying to present a simple wave profile. Then the particle vibrates from the origin up, down, moves up again, and then down, then maybe ends at this point. So this defines the x direction in a given time, all right? That's for the particle. Then this is the origin of the particle. This represents the vertical component of the vibrating particle, all right? Okay, if we assume the particle to have vibrated up to this point, okay, this is the vibrating particle. It vibrates in vertical direction, okay? So the distance of the particle from the origin is given by this letter x. By this letter x, okay? So that's the distance of the particle from the origin. Now the wave is moving from left to right. That is what is happening here. All right, the maximum displacement of the wave particle is shown as follows. This is the maximum displacement, okay? And this is referred to as the amplitude. Amplitude, all right? Okay, that's maximum displacement. Okay, there is also downward maximum displacement, which is also referred to as the trough, okay? Right, so that is what it means. So this point is known as the crest, this is known as the trough. All right, having said that, the next thing we need to understand here is a crest and a trough give a wavelength. So that completes a circle. A cycle. So we have that, as you can see, this is a wavelength, okay? A crest and a trough makes a complete cycle, and that gives a wavelength. All right. Then the next thing we are going to consider is the phase difference. Okay. The particle was disturbed from the origin, and it vibrated until it gets to this point, right? Now there is a distance between the origin and the point where the particle is now. So there is a kind of difference, okay? And that is what we refer to as the phase difference, okay? Now, if we look at the phase difference, this is the crest, a semicurve. This is the trough, another semicurve. So a crest, a trough make up a wavelength. So we have 2 pi there, okay? Then the next thing is we consider the distance that has been attained by the vibrating particle, and then the wavelength. That is x all over this. And this finally will give us a 2 pi x all over wavelength. So this represents the phase difference of the vibrating particle, right? So this represents the phase difference of the vibrating particle. Now, having said that, we need to analyze, or rather find, the angular speed of this vibrating particle. So how do we get that? Of course, any body or any particle performing a cyclic motion or cyclic movement sweeps across equal angles in equal time, okay? So we need to understand that. And the speed it undergoes, or the velocity it undergoes in doing that, is what we refer to as angular velocity. This is angular velocity, omega. So we need to look at the angular speed or velocity of the vibrating particle. That is this, right? So we use omega, the Greek word omega, as theta all over t, which is also 2 pi, all right, all over t. Then by the time we look for the relationship between t and f, that is time and frequency, we will arrive at 2 pi f. Therefore, the angular speed is given as 2 pi f. All right? We have another relation that will help us to solve whatever question that will come up from this. Okay, so that is for this. Then we need to also understand that these parameters, y, x, they represent something meaningful. Y is the vertical component or coordinate of the vibrating particle. Okay? Yx is the horizontal component or coordinate of the vibrating particle. It also shows the direction the vibrating particle takes. You can see. So the vibrating particle is traveling from left to right. It's traveling from left to right. Okay? According to the wave motion you have seen on the board. Alright, having said that, now we have certain parameters that will help us to generate what we're looking for. The next thing is we consider the fact that what we have on the board is a sine wave function. It's a sine wave function which can be represented by y, the vertical component, the amplitude, okay, sine omega t, all right? That is a sine wave function. That's a relation that represents sine wave function. Now, with that in mind, you will understand that I said earlier that there is a phase difference. There is a phase difference simply because the particle vibrates from left or travels from left to right, okay? There is a phase difference which will assume a negative sign. So, the phase difference now is being incorporated into the relation as omega t minus phi, where phi represents the phase difference. All right, so why the negative sign? Let me explain. Why the negative sign? It means the vibration of the particle at this point, P, okay, lag on that at the origin, O. So that's why the negative. That is the essence of the negative, okay? Because the particle is traveling from left to right. If it is traveling in the opposite direction, maybe from right now to left, the sign would have been positive. All right, so having said that, the next thing we are going to do is to substitute these parameters that we have carefully generated where necessary, where we have omega, that is angular speed, and the phase difference, we substitute accordingly. Then we have that gives this way, goes this way. For angular speed, you have 2 pi ft minus, then for phase difference, we have 2 pi x over wavelength. 2 pi x over wavelength. All right. If you a very close look at this relation, you will see that there's something common, and that thing common is just 2 pi. So we bring it out. Sine 2 pi comes out. Then inside we have the ft, that is frequency, times 10 minus what? X all over wavelength. All right? Okay. Now we need to recall. That's for this now. We recall that v, or rather the speed of light, c, is equals to wavelength, the product of frequency and wavelength. So from there we can get that frequency is also speed of light over wavelength. So we substitute. Where we have frequency in the relation, we substitute, okay? We now rewrite the relation as y is equals to amplitude sine 2 pi brackets. In place of frequency f, we substitute with c, speed of light, over wavelength. That is c over wavelength, and then t minus x all over wavelength. Okay? All right. So we are making progress here. So that is it. Then something also is common here. That's wavelength. Wavelength is common here. So we bring that quickly. We have A, that is amplitude, okay? 2 pi now, all over wavelength, that is common, bracket CT, this is CT, right? Minus X, okay? We call this relation X-series. We mark it X-series, all right? That relation with X-series represents a plane progressive wave equation, okay? Look at it, very clear. All right, from there, we can still generate more. Another type of plane progressive wave equation. Let's see how it works out. All right, so that's for that. We move on. With this, we'll recall that omega, or angular speed, so to say, angular speed, as we have stated before, is given as a 2 pi f. Then our relation is amplitude sine 2 pi over lambda brackets CT minus X bracket close. That's what we had in the first place, right? Now, if we go back, then recall that frequency, once again, frequency, by rewriting this equation back to its original form, we have 2 pi, okay, brackets ft minus x over lambda. That's the original equation we had here in the first place. Yeah, what we had in the first place at this point. So what we need to do for frequency, we recall that frequency is also taken as f is equals to 1 all over t, right? The inverse of time is also frequency. So we can substitute there. So we'll rewrite this. Amplitude is equals to sine, all right? 2 pi, all right? Bracket. In place of frequency f, we substitute with 1 over t. That is a small t now over capital T minus what? X all over wavelength. All right? Look at this once again. This another, we call this relation X-series 2. Okay? Look at this once again. You will see that this is another plane progressive wave equation, which is also different from the first one we found. Look at the first one we found, and look at the second one. Okay? So, the X-series, the first relation, and these are two plane progressive wave equations that can be used to find the following parameters. We can use any of these to find the frequency of the vibrating particle. We can as well use it to find the wavelength, the speed of the wave particle, the amplitude, the time, and so on and so forth. That is the beauty of this whole thing. All right, having said that, my dear friends, I urge you to subscribe to our channel. Follow us on our social media handles such as Twitter, Instagram, Pinterest, or Reddit, Likey. You can as well like us on our Facebook page, and you will see many